So in my last video I described how you could drive many SPI devices from a Raspberry Pi. So on this board I've got 5 SPI devices including a display, which is an SPI device. In this video I'm going to describe a Linux driver which I've written for it, which you can actually call from a Python script, so you can control many SPI devices from a Python script. I'll go through how to control each of these devices. So the display at the top, then I've got GPIO extenders there on 2 different addresses, and then I've got A to D converters at the bottom, and I will use the test boards that I was using in the last video as well. And I'll take you for an example of driving each of these in a separate section on the video. So first of all, I'd drive the SPI display from a Python script, then I'd drive the GPIO extenders from a Python script, and then the analog to digital converters from a Python script. So all of these Python scripts I've put on my GitHub page under Raspberry Pi Python interfacing. So when you go into that, there's a subdirectory now called RPI SPI, and go into that and it shows you the scripts that I've produced. So the top one, this is for the GPIO port expander, which is the microchip MCP23S17. The next one is the MCP3008, which is a 8-channel analog to digital converter. The next one is called RAW, because if you want to drive an SPI device which the driver isn't actually programmed to do, you can actually use this RAW mode and look up on data sheets what commands you should send, and you can program it like that. So it should cover most SPI devices doing it like that. But I'll demonstrate calling one of the analog to digital converters through the RAW device so you can see how that works. And then lastly in the scripts is the SSD 1306, which is a 128 by 64 pixel OLED display, and that's the first one that I'll demonstrate. So first of all, I'll show you the driver before we get to any Python code. So the driver is called RPI SPI, and what you can do is it creates a device in the dev folder, which is the root device for the driver, which is just called RPI SPI. So if I show you what's in that, that shows you the configuration of the driver, and it shows you the chip select number at the start, so you can identify which each device is, and then the address of the device if the device supports addresses. So for example, these GPIO extenders, they support addresses. They give you the device name, so you can see that as well. And it also creates a file in proc called RPI SPI, and that shows you the current status of the device. It tells you what the chip select allocations are on the Raspberry Pi GPIOs. So I've got chip select 1 configured to pin 25, but the other ones I'm not using because I'm using a 2 to 4 decoder, so I don't need any more chip selects. But there's a data select pin for the display configured on pin 22, and it's just saying at the end that the chip select on the Raspberry Pi for the standard SPI device is the standard CS0, and it gives you a list of all the devices below that, and each device has a set of registers. So the A to D converters have 8 registers, 1 for each of the A to D channels. The raw SPI device, which I'm calling raw, just has 1 register which you can write to and read from to do the raw device stuff. Then the display, you can only write to that, so there's an init register to initialize the display, and then a write register. And then the GPIO port extenders have a bunch of registers. If you look in the data sheet, you can see what each of those registers is, but you just read and write values from those registers. So the other thing about this driver is, if I show you in dev, so this is like I said before, this is configuration, but you can reconfigure this on the fly. So I've got a file called device.cfg, and it's only got 3 configured 3 devices in that, whereas the current configuration has five devices. So if I cap, oops, if I cap that contents of that file into the base device for the driver. Now if I go show you what's in how the driver's configured, it only has the 3 devices which are in that file. So you've got A to D converter, the display, and then the GPIO extender. So it can be reconfigured on the fly. So and then the other thing to point out about this is, so it's got 3 devices configured, but each of those devices has a set of registers associated with it. So if I look in the dev directory at all of the devices called RPI SPI, it shows you that each device you can identify with the chip select number and the address of the device and the device type, and then it has the register. So each register has its own device in the dev directory, so you can read and write to the registers, and I'll show you in Python later on how that's used to communicate with each SPI device. But if I put it back to the default configuration, and now if I list all the devices again, so there's a lot more registers now. So you've got all 5 devices with each register, and this is the configuration I use to demonstrate the Python code. So the first set of Python code that I'll demonstrate is for the display. So if I just run this Python script, and you'll see on the display it comes up with a random set of data, and what it does is it inverts a random set of data. So you see the random set of data change, and then it just displays this, which is kind of a test screen. So at the top you can see the time and date, which is updating constantly. Then there's some text, so example text output. Then the first bit of graphics on the left is lines being drawn in different directions. So I did that as just to test my code. Then there's a point which is plotted to the right of that. And then there's a filled square, and that's inside a non-filled square, and then a filled circle inside a non-filled circle. So I'll go through the code as how which does that. So on the code, it's this piece of Python code here. So at the top I've got definitions for what each of the registers numbers are, so I can just refer to them as constants. And then there's a function, and this does communication with the device itself. So data information gets passed in as this args, which is a variable length field, so you can send in many bytes of data. It just builds up a message from an empty string. It goes for each of the arguments which is passed in, and it checks to see if it's a string, if the argument type is a string. If it's a string, then it just concatenates a string to the message. Otherwise it's a numeric value. It'll be an integer, because I'm only dealing with integers and strings. And so in the case that it's an integer, it takes the actual value of the integer, and it uses this pack command, which converts the binary of the integer, the actual value in memory, and adds it to the message, so I can send it to the file. And then I write to the device file the message. This device file is in this example is always open, so it just has a reference file. The actual file is opened in the main body of the program, which should come to down here. This can be ignored, this first bit. This is just so I can get keys from the keyboard without key presses, without waiting around, so that I can, when a key is pressed, we can exit the program rather than leave it running infinitely. So here I open up the device. So this is one of the devices, which is the RPI SPI device drivers. So this is chip select 010 and address 0, and this is the device which is the display SSD 1306. It's open for writing as binary, and then this is a call to the function which I described up here. So that was called do display, and So all the communication do with the screen for this is you just call the do display, and then you send it the constant that you want to be sent, and any additional data. In some of these, like this command, there's no additional data. So what this is telling is telling the display to be turned on. And we're setting the contrast on the display to 127, so the contrast value is from 0 to 255. So we're setting the contrast halfway up. We're filling the display with random stuff. This is just this function is in there just because I used it as a test function when I was writing the original code, so I just left it in there. Then we wait for a second, and this is just to test the screen inversion. So in the command set for the display, there's a way you can just invert the display, so that's in there as a thing. So the random data will invert, and it just makes it look like it comes up with more random data quickly. Waits for a second, then we turn it back to non-inverse display, and we call the clear display. So we just tell it we want an empty display. So in a program you'd normally probably just call CLS at the top. You wouldn't do all this other stuff which I've just done as like an example as to how to call these functions. Now we get to functions where we actually want to pass in values. So I'm going to draw, this is where we draw the first of the lines, and then this is X position 1, Y position 1, and then X position 2, Y position 2, and then at the end it's effectively the actual argument is color, but really it's a two-tone display, so it's either black or white sort of thing. So you can draw lines and then you can erase lines by doing them as color 0. Which can come in handy, and I'll probably have a program to demonstrate that. Then we just draw all the other lines going in different directions to make up a kind of a polygon. Then we plot a point, and then we pass in X and Y and the color of that point. And then a box with the 4 corners. So this is X1 top left hand corner, and sorry, bottom right hand corner, and color. Then filled box, again top left hand corner, bottom right hand corner, and color. A circle, and this is X and Y position, and then this is the radius of the circle, and then a filled circle, again X and Y position and the radius. And it's as simple as that to do communication with the driver. So you select the device type that you want, and then you've got all these things that you can just send it in a program. And the rest of this program is just me dealing with just doing an example. Oh yeah, and actually displaying the time and date as well. I'll go through that. So this is the loop, and rather than it being an infinite loop, rather than it being an infinite loop, it just waits for this exit flag to be changed. So this just delays for 1/5 of a second, gets a key, and if a key's been pressed, then it sets it to exit the program. So we get the current time and date, and then all we do, so this is a different function, so this is for doing text. We have the print command, and we have X and Y position. So this is slightly different. So X is actual pixels across the screen, but Y is lines 1 to 8 down the screen. And then format some text to display there, and then this is just another print statement below that. Right, and so we get down to this point, and actually if we stop the program at this point, the display wouldn't contain anything still, because all I'm doing is I'm updating a local buffer up to this point, and then at this point I tell it to update the display, and that makes for a crisper, sort of quicker process when you're actually doing the programming. You don't see these things appearing on the screen as they're drawn. You just see it come on the screen at the last minute when we actually just send all the data to the display. So, and that's something to remember, is that if you're using this, you must always remember to do an update, because if you're sending these commands you're thinking nothing's happening on the screen, it's just because an update hasn't been requested. And then finally, as after we come, so this is outside the loop now, the main loop, and we just turn the display off, and we close the device file, and this cursor's we just put it back, so the terminal behaves kind of normally when we come out of this program. So the next program we'll take a look at is the analog to digital converter. And that's the MCP308. So all this is doing is it's just reading values from the analog to digital converter. This converter is just hooked up to the flip-flop, so you see the green and red LEDs which are flashing. All it's doing is reading values from that, so it doesn't really sort of explain much at the minute, but as I go through the code you'll see what it does. So if I hit a key again, it'll come out of there. I go into the code. It's very similar the way that it communicates. So I've got just at the top a function which does the communication with the driver. So this one's slightly different in that it takes the device file name, it opens it as read binary rather than writing this time, and it reads 4 characters, which is an integer size. So it reads 1 integer, and it closes, and it just stores that in data for the time being. And then what it returns is it unpacks that integer in it unpacks what is 4 characters basically into an integer, and just make sure it only returns the first integer. If there was more than 1 integer, it just returns the first. So we only reading 1 integer at a time, and then the rest of this stuff I'll skip over the stuff I've already explained, which is just the surroundings of the program. So this is different in that I haven't had to open a file. That's all done in the routine that we saw above called read AD. But we pass in the device name, and the reason we pass in the device name is because each channel on the ATD converter is in a different device. So I read back each value into different from each channel into a different variable. I just get the current time and date as well, because I like to display the current time and date. And then I just display the values of each of the A to D converters on the display, and that's as simple as that. So what you're looking at really is just this code here to read all 8 channels and display them on the display, and then this function just to do the device driver communication. So this one's a bit more interesting. It's the for the analog to digital. I'll go read it again, but using the raw device on the driver. So this is how you would read or write to devices which aren't in the analog to digital converters and GPIO expansion and the display, which I've currently got configured in the driver. So anything else, you would use something like this. And see, again, it's just displaying exactly the same figures as in before, all channels on the A to D converter, but they're all connected up to this potentiometer. So if I turn it right down, it goes down to 0, and as I turn it up, the values increase until it gets up to the top of the values. It goes up to 1023. So 0 to 1023, it reads the potentiometer. So I'll explain how this works. So I go into the raw device. Again, I'll skip over all the surrounding codes the same, but this time we've got 2 functions, because with the raw device, what you usually have to do is write an instruction, which my device driver would normally do for the devices it knows of automatically. But this time you're going to have to look up in the datasheet what the instructions are supposed to be, and then you read back the value that's returned from that instruction. So the read value function's here, and it's kind of the same as in what we saw in the last A to D converter one. It just opens a file for read as binary, but this time it's going to return a set of integers. I've just put 256 here, so you could increase that, but it reads up to 256 integers into the data function, and this time the data is split into sets of integers, which is returned as a list of integers. And then to write to the device, it's like on the display function we had earlier, but it's slightly different. So this time I'm passing the device file and the arguments, and I'm creating a message again in the same way that I did in the display driver, and I'm just adding strings if they exist as standard strings, and then I'm adding integers again added to the string as a converted set of binary data. And at that point then I open the file as writing as binary, we output the message and then close the file. So if I get to the actual communication code itself. So with this, you specify the device name and the register. So the device is always SPI raw if it's a raw device, and there's always just one register for that device, which is reg raw. And then you just put in the bytes afterwards, and they have to be passed as bytes, as individual bytes. And then, so after writing that, you can then read whatever value was returned from that. So you open up exactly the same device as you had up here, but for this time we're going to be reading from it, and the value comes back as a set of integers in a list. So it's up to you then to interpret how those are fed back. So I know the first value is the most significant byte, but it's only the bottom 3 bits of it are significant for us, so we just mask out the rest of it, and we multiply that by 256 because it's the higher order of the bytes. And then we just add the value of the lower order of the bytes, and you get the analog to digital conversion value. So in theory you should be able to drive most SPI devices through this method, but it's always possible there might be some that you can't do. But we just do that for each of the channels of the A to D converter, again getting each value back in its own variable, and at the bottom just displaying the A to D values that I read back. So a bit more complicated than the other ones, because you have to know what's in the data sheet and how to send each byte and how to interpret the bytes that come back. But it's reasonably easily doable through Python. So this last example Python code is for the GPIO port expander. So it gives you an extra 16 GPIO ports. And so if I just run the example program first, and it's just returning. So I've got 2 devices. I've got one on address 0 and one on address 1 on the board. So that's 2 chips I've added. This first one on the left, you can see, is returning the values which are coming back from this output. So I'm outputting some of the on half of the bits onto these LEDs, but when you read the port, it actually shows you the values coming back in the port. And then the second port over there, some of them are tied up to the flip-flop, so sometimes you might see them one go high or low, but not very often. But the lower and upper values, I've got some keys that I've added to the board, and as I press the keys, you'll see that the other device responds to me pressing the keys. And then I just press the key to finish the program. So I'll go into that. Skip over again most of this stuff. So this one I've got definitions at the top again as to what each of the registers is. I've given a little explanation, so you can go to the data sheet to find out more about this, but this is probably one of the most important registers, is the IO direction. And if you configure a bit to be 0, it's an output bit, and if you configure a bit to be 1, it's an input bit. But then you can go for all of these others. So I guess I'll highlight the most important ones are the write, so if you want to write outputs to the GPIO device, the read if you want to read the GPIO device, the IO direction, and then there's one more, and that's near the bottom, so the pull-up resistors. So you can tell the device to have pull-up resistors. The other registers, I'd go to the datasheet and read up on those if you need anything more detailed than that. Again, this time we've got 2 helper functions, one for reading from a register and one to write into a register. So all it gives you when you read is you pass in the device name. It opens up the device for reading binary. Again, it just reads one integer value, which is 4 characters, and it compacts those characters into an integer and just returns the first one if there happen to be more than one. And then the write-in, again you pass in the dev file and the arguments you want to send, and it builds up the message like it did in the previous ones by saying if it's a string we just append the string, and if it's a byte value, an integer value, it then just breaks that down into the 4 characters it needs to add to the message. And then we open the device that we want for writing as binary, and write the message out and close the file. So it's fairly simple. So up the top I've got the bits where I've got two chips. So this one's on chips. They're both on chip select 011, but this one has an address of 0 and this one has an address of 1. And so the devices are both the same name, but this is me setting up the registers at first. So I'm setting up the I/O direction to be half inputs and half outputs. You probably don't need to know about this. Is in the input polarity. You can switch to polarity. I think I've done that there. I don't know why I did that. Probably just as an example of using that register. Really, I think I just did an example of using all the registers because I'm just resetting. You don't need to reset these to zeros, but you can if you just want to be complete. Then I just have pull-ups on my inputs, not on my outputs. Not that I think the device is intelligent enough to know not to put it on the outputs if you asked it to. And then I set up the second device in exactly the same way. But these are all inputs that I've got on the second device. And the buttons are so I'm putting pull-ups on the first 4 bits and the last 4 bits because that's where I've got the buttons, which I was demonstrating. So that's configuring the device, and then further down, what I'm doing here is I'm just setting a bit and then rotating the bit through the register so that you saw those LEDs switching between the bits. So there I'm just sending the output, writing it to that device. Again, just getting time date to log the time and date, but I'm reading the GPIO value for the first device, GPIO value for the second device into different registers, and then I'm outputting them, but I'm using the Python convert to a 16-bit binary value on the display, so it comes out in binary. It's a bit easier to understand when you're demonstrating like this, but you could bring it back. It comes back as an integer, so you can use it as you like, sort of thing. But that's the final Python demonstration. And so next I'll do some kind of program to demonstrate as well.